Welcome to lecture 30 on essentials of topology. In this lecture 2, we will continue the study of continuous functions. Specifically, we will study the concept of continuous functions associated with relative topology, quotient topology, and product topology. Before starting to study these concepts, let us study a concept which is associated to the concept studied in the previous lecture, that is characterization of continuous function in terms of closure. Actually, in the last lecture, we have seen a characterization of continuous function, that is if f is a function from topological space x tau to y tau dash, we say that this function f is continuous if and only if the characterization was f of a closure is subset of f a closure for all a subset of x. A natural question is, can we characterize the continuity in terms of inverse image as well as closure? Answer is yes, we can do it. What exactly we will do, that we will take some subset of y and we will try to take inverse image of this b plus use the concept of closure to characterize the continuity of this function. The statement of this theorem is as given, that is if we are having two topological spaces x tau and y tau dash, then the function f from x tau to y tau dash is continuous if and only if closure of f inverse b is subset of f inverse b closure for all b subset of y. In order to prove this theorem, let us first assume that f is continuous. Now, in order to prove it, let us begin with, as b is a subset of y, we know that this b will always be subset of its closure, and therefore what about this f inverse b, that will be a subset of f inverse b closure. Now by taking the closure, we can conclude that f inverse b closure is subset of closure of f inverse b bar, as we already know that if p is subset of q, closure of p is subset of closure of q. Now one more thing is here, that is this b is subset of y. What about this b bar? Note that this is tau dash closed. If this is tau dash closed, as f is continuous, so f inverse b bar is tau closed, and therefore by the concept of closure, the closure of f inverse b bar will be same as f inverse b bar. Therefore we can write closure of f inverse b is subset of f inverse b bar, and that was our requirement. So this is the proof of first part. Moving ahead, now let us assume it that for all b subset of y, closure of f inverse b is subset of f inverse b closure, then we have to prove that f is continuous. In order to prove that f is continuous, just see the assumption which is given in terms of closure. Therefore, it will be better to use the characterization of continuous map in terms of closed set to justify it. Accordingly, let us take a subset f of y which is tau dash closed, and if this is tau dash closed, we can conclude that closure of f equals to f. In order to justify the continuity of f, what we have to prove? Actually, we have to justify that this f inverse f is tau closed. In order to justify it, we have to prove that this closure of f inverse f is equal to f inverse f, or this is equivalent to two statements. The first one is that f inverse f is subset of f inverse f closure, and the second is f inverse f closure is subset of f inverse f. Note that first follows from the definition of closure. So what exactly we have to justify? We have to justify only the second one. In order to justify it, now come to the assumption and replace this b by f. So from here we can write f inverse f of closure is subset of f inverse f closure, but note that f closure is equal to f, so this can be written as f inverse f, or that closure of f inverse f is subset of f inverse f. Therefore, this second also holds, or f inverse f is tau closed, that is inverse image of tau dash closed set is a tau closed set, and therefore f is continuous. Moving to the next, let us see the continuous function from a subspace to a topological space, and that function is precisely inclusion function. Let A tau A be a subspace of a topological space X tau, then what we can prove? We can prove that the map I, which is from A tau A to X tau, is continuous. Note that this function I is from A to X, defined as Ix is equal to X for all X belongs to A. We can visualize this function. This is something like, if this is a set A and another one is X, so this is our A, this is X, and A is inside X, and we are defining this inclusion function from here to here. We are sending this X to Ix. Now, if we want to prove that this function is continuous, let us take g belongs to tau and try to compute I inverse g. Note that this I inverse g, that will be nothing but this is collection of all those x belongs to A, such that I of x belongs to g. That is, this is collection of all those x belongs to A, such that x belongs to g, or this is collection of all x which is common to A as well as G, and therefore this can be written as A intersection G. But note that A intersection G is always a member of tau A. Thus, inverse image of tau open set is a tau A open set, and therefore this map I is continuous. It can be visualized from this diagram too, that is, if we are taking a set G here, then if we want to find out what is its inverse image, so its inverse image will be something like this portion contained in A. That is, if this is our G, then this is I inverse G. Moving to the next one, we have seen that this inclusion function I is continuous when the topology on the domain is the relative topology, but note that we can also justify that the relative topology is the smallest topology on A, which makes this inclusion function continuous. In order to justify it, let us take this inclusion function from A to some tau dash is in the topology, to this x tau, where this tau dash is any arbitrary topology on A provided this I is continuous. Now, if we want to justify that this relative topology is the smallest topology, what exactly we have to justify? We have to prove that this tau A is always coarser than tau dash. In order to justify, let us see if we are taking any g belongs to tau, we have already seen that this I inverse g is given by A intersection g. And because this function I is a continuous function, therefore this belongs to tau dash. But at the same time, it is to be noted that for all g belongs to tau, this A intersection g is always a member of tau A. Thus, what we can conclude from here, that is for all h, which is A intersection g in tau A, this H will always be member of tau dash, or this tau A is a topology which is coarser than tau dash, that is this relative topology is the smallest topology on A. Before moving to the next concept, let us discuss about the composition of continuous function. What we can justify that composition of two continuous functions is a continuous function. In order to justify it, let us take a function f from topological space x tau to y tau dash, and let us take another function g from y tau dash to a topological space Z. Let us take this is tau double dash. This is given that f is continuous function. Also, this g is a continuous function. What we have to deduce, that we have to show that their composition, that is g composition f from x tau to z tau double dash, is also a continuous function. So we have to justify it. Now, in order to justify it, let us take any open set with respect to topology tau double dash. So let us take g belongs to tau double dash. Now we are computing the inverse image of this g under g composition f. This is precisely f inverse of g inverse of g. Now let us use the continuity of f as well as g. As f and g are continuous, what we can deduce, let us see through this diagram, that if this is our x, let us take another set y, and let us take another set z. This is x, y and z. Now if we are taking an open set here, let us take this is an open set G, as the map from x to y is f and the map from y to z is g. Let us compute inverse image of this G, and that will be given by G inverse G. So this is precisely G inverse G. Now if we are finding the inverse image of this G inverse G under f, so this will come to here, and this will be f inverse of G inverse G. It is to be noted here that if G is open with respect to topology tau double dash, this G inverse G will be open with respect to topology tau dash, and this f inverse of G inverse G will be tau open. So actually this is tau open, and if this is tau open, it means that inverse image of every tau dash open set under this composition is tau open, and therefore this composition is a continuous map. Moving ahead, again coming to the concept of subspaces, let us take a subspace A tau A. This is a subspace of x tau, and take a continuous function f from x tau to another topological space y tau dash. Then the restricted function f over A, which is defined from A tau A to y tau dash, is also continuous function. Note that this function is defined as, this is f over A is from A to y, such that the restricted function over A at x is equal to f of x for all x belongs to A. In order to prove that this is a continuous function, let us see an interesting thing here. This is already given that f is a continuous function from x to y. So this function is from x to y. Also, we can define an inclusion function from a to x, as a is a subset of x. Note that this is f from x to y. Now let us take their composition. So their composition is f composition I, and if we are trying to find out f composition I at any x, this will be nothing but f of ix. This is f of x, and note that this x belongs to A. That is, this is the restriction of f over A. Meaning is to say that this function is nothing but composition of f and I. But note that this f is a continuous function, and also inclusion function is a continuous function, which we have already seen. Therefore their composition is a continuous function, and hence this restricted function is a continuous function. Moving to the next concept, that is the concept of quotient map. We have already seen that if a topological space x tau is given and A is any non-empty set, and if we are having a surjective function q from x to A, then by using the topology on x, that is by using this topology, we can put a topology on A with the help of this quotient map, and this topology is known as quotient topology. Just recall the definition of this topology. This topology was defined as collection of all those subsets of A such that this Q inverse G belongs to tau. Now if we want to justify that this map is a continuous map, actually it is trivial from the definition of quotient topology itself, because if we are taking any G belongs to this tau Q, it means that Q inverse G belongs to tau. That is, inverse image of tau Q open set is a tau open set. Therefore, this map is a continuous map. Also, if we want to see the nature of this quotient topology in terms of its size, then actually this is the largest or finest topology on A for which the quotient map Q is continuous. In order to justify it, let us take this map Q from x tau to A tau dash, where this tau dash is a topology on A such that this Q is a continuous map. Our interest is to justify that the quotient topology is the largest topology. So what exactly we have to prove? We have to justify that this tau dash is coarser than tau Q. It can be easily justified here, because if we are taking any G belongs to tau dash, by continuity of this Q inverse G belongs to tau. And note that if Q inverse G is a member of tau, from here, by definition of quotient topology, G belongs to tau Q. That is, tau dash is coarser than tau Q, or this tau Q is the largest topology on A. Moving to the next concept, let us see the continuous maps associated with product topology. We have already seen the concept of projection maps. The concept was, if we have two topological spaces x1 tau 1 and x2 tau 2, and let us take tau be the product topology on x1 cross x2, then the map defined as, this is the map pi 1 defined from this topological space, that is x1 cross x2 along with product topology to x1 tau 1, such that pi 1 x1 x2 is equal to x1. Similarly, the second projection map, that is pi 2, is defined as pi 2 x1 x2 equal to x2. What we can justify that both the maps are continuous. In order to justify it, let us take the case of this pi 1, and if we are taking any g1 belongs to topology tau 1, let us compute the inverse image of this g1 under pi 1. So this will be the collection of all ordered pair x1 x2 such that pi 1 x1 x2, that is, this is ordered pair, this belongs to g1, or this is collection of all such ordered pairs x1 x2 such that x1 belongs to g1, or this can be written as g1 cross x2. Note that this set g1 cross x2 is a member of product topology. Therefore, this pi 1 inverse g1 is tau open, that is, inverse image of tau 1 open set is tau open, and therefore this map, that is pi 1, is a continuous map. Similarly, if we are taking any g2 belongs to tau 2, we can justify that this pi 2 inverse of g2, this will be nothing but x1 cross g2, and which belongs to tau, and therefore this map is also a continuous map. Moving to the next one, an interesting fact about the product topology is that the product topology is the smallest topology on this x1 cross x2, for which the projection maps pi 1 and pi 2 are continuous. In order to justify that this product topology is the smallest topology, let us take a topology or any arbitrary topology tau dash on this Cartesian product of x1 and x2, so that the projection maps pi 1 and the projection map pi 2 both are continuous. Then what we have to justify? Actually, we have to justify that the product topology, that is tau, is coarser than this tau dash. Recall the fact which we have already seen, that if we are taking this collection as b dash, that is pi 1 inverse of g1, where g1 belongs to tau 1 union pi 2 inverse g2, where g2 belongs to tau. We have seen that this collection is a subbasis for product topology tau. In order to justify that this tau is coarser than tau dash, the first step which we are going to justify, that this b dash is contained in tau dash. In order to justify it, let us take any g belongs to this b dash, then what will happen? This G will be either of the form pi 1 inverse G1, or this G is equal to pi 2 inverse G2 for some G1 belongs to tau 1 and G2 belongs to tau 2. But note that as pi 1 and pi 2 are continuous, so if we are taking any G1 from here, its inverse image, that is pi 1 inverse G1, this will be a member of tau dash, and in the same way if we are taking any G2 from tau 2, this pi 2 inverse G2 will also be a member of tau dash. Therefore, in any case whether G equals to pi 1 inverse G1 or this is pi 2 inverse G2, G will always be a member of tau dash. Hence, this B dash is contained in tau dash. Also, as this B dash is a subbasis for product topology, tau, we can find a basis from it. Let us take that basis be B. Now if we are taking any B belongs to this basis, what will happen? This B can be written as finite intersection of members of subbasis, that is Bi belongs to this B dash. But what we have already justified, that B dash is contained in tau dash, it means that this B is finite intersection of members of tau dash, and if it is so, we can conclude that B also belongs to tau dash, that is basis itself is contained in tau dash. Finally, if we want to justify that this product topology is coarser than tau dash, let us take any G belongs to tau and any element of this G. Because this B is basis for product topology, we can find a member B in this basis such that X belongs to this B and this B is subset of G. But note that if B belongs to B, B also belongs to tau dash because this basis is inside tau dash. So what we can conclude from here, that for all X belongs to G, there exists a tau dash open set B such that it holds, that is X belongs to B is subset of G, and from here we can say that this G is tau dash neighborhood of X, or we can say that G is tau dash neighborhood of each of its points. And if this is neighborhood of each of its points, we can say that G belongs to tau dash. Hence, this tau is coarser than tau dash, or the product topology is the smallest topology for which the projection maps pi 1 and pi 2 are continuous. These are the references. That's all from this lecture. Thank you.